So we've discussed solutions and the way that they're formed, energetically speaking. So now we're going to look at the factors that affect the solubility, or the ability of a solute to dissolve into a solvent. So first factor is the nature of the solvent and solute. So polarity, charges, things of that sort. The next thing that's going to affect solubility is temperature, and the last thing is pressure. So, solute-solvent interactions have been discussed previously when we were discussing our delta H of our mixture. Okay, and basically, the more likely that the interactions are attractive between your solvent and solute, the more likely a solution will form. So, when two substances have similar intermolecular forces, they're going to be more likely to be soluble in one another. And that brings us to the like dissolves like concept. So, salt dissolves in water, but oil doesn't mix with water. And that's because oil is nonpolar, water is polar. And salt, salt forms ions, which are going to be attracted to the polar portions of the H2O molecules, and that's why the sodium chloride solution will form. So if we just kind of look really quickly, so nonpolar molecules, they're going to be soluble in nonpolar solvents. So carbon tetrachloride and benzene, they'll dissolve into one another. Polar molecules are going to be soluble in polar solvents. So alcohols will dissolve into water. And ionic compounds are going to typically be very soluble in polar solvents. These processes, or this intermolecular force determining factor, is one of the big indicators of if solutions will form. And we already looked at this, as I said, when we looked at our delta H of our mixtures, and how it corresponds to the overall delta H of solution. So if you have similar intermolecular forces, you have a good chance of a solution forming. So now that's not to say that solubility is always going to be only dictated by a polar moment on the molecule. So in this case, we have a bunch of straight chain alcohols, methanol, ethanol, propanol, etc., all the way over to hexanol. And if we look at the solubility of H2O, of the alcohol solubility in H2O, notice that the first several are very soluble, but as we continue down and as we get into longer and longer chains attached to the OH alcohol group, solubility decreases. And in the flip side of that, if we look at a nonpolar solvent and basically look at the solubility aspects as we decrease or as we increase the chains associated or attached to the OH group, our solubility increases. So the concept here is that those solvent-solute interactions are going to be affected by the overall characteristics of the molecule. So when we're looking at, say, methanol, okay, we have an OH group, which we know is a very polar group capable of hydrogen bonding, and we have CH3 being the other component of this. Now, the difference in electronegativity between carbon and hydrogen is very small. So this region of the molecule is nonpolar, while this region of the molecule is polar. So you notice when we're looking at the solubility of these alcohols in water, the smaller the nonpolar portion, the more soluble the alcohol will be in a polar solvent, and in this case specifically H2O. Okay, so as the nonpolar regions increase and get larger and larger, the solubility is going to decrease. And then on the flip side of that, as the branch or the chain portion, the nonpolar chain portion of the molecule increases, the solubility in nonpolar solvents is going to increase. So we can't just automatically assume that we're going to have solubility just because we have a specific type of group that confers a region of polarity. We do have to look at the overall molecule. However, generally speaking, we don't typically deal with very large chain alcohols in terms of solvents and things of that sort. They're usually used for extraction and things of that sort that we don't do in this class. So they want us to predict whether the substances that are being shared here are going to be more soluble in carbon tetrachloride or water. So carbon tetrachloride is a nonpolar solvent, and obviously water is a polar solvent. So what we're going to look at is the individual molecules here and decide which one or which ones are most like the nonpolar solvent and which ones are most like the polar solvent. Okay, so let's go ahead and let's look at what we've been given. C7H16. Okay, we know that this consists of carbon and hydrogen atoms, so we know that it's going to be a nonpolar molecule, just like we discussed in the nonpolar portion of the alcohols in the previous slide. Okay, Na2SO4 is basically an ionic compound, so it consists of ions. So of course they're inherently charged, so this is going to be a polar molecule. Okay, HCl, there's a large electronegativity difference, so polar molecule. And I2 consists of two of the same types of atoms, so this is a nonpolar molecule. Okay, so I2 and C7H16, these are both nonpolar molecules, so the whole concept of like dissolves like means that carbon tetrachloride is going to be the solvent. Okay, and in that same thought process, our sodium sulfate and our hydrochloric acid, those are both going to dissolve well in the polar solvent, which in this case is H2O. So with these problems, just make sure you're identifying polar and non-polar solvents, differentiating between those two, and identify the polar and non-polar solutes, and basically match them up in that manner. Okay, so the next thing we're going to talk about is temperature and solubility. Temperature affects the solubility of a solid in a pretty general way. There are some exceptions to these rules. However, generally speaking, as you increase the temperature of the solution, the solubility of the solid is going to increase. So I can dissolve more sugar in hot tea than I can in cold tea. And that's generally speaking true. We see that on this solubility chart here. Basically, these are our temperatures. These are the amounts of solutes that we can dissolve into a specific amount of solvent. And notice most of them increase as you increase the temperature. Now, there are a few exceptions to the rule. However, generally speaking, you could go with solids being more soluble at higher temperatures. Now, this same temperature and solubility approach to gases is very different. So what we see is that as we increase the temperature of a solution containing a gas, the solubility of that gas is going to decrease. So this is actually one of the things that contributes to thermal pollution. Around, like, say, power plants, basically there's water that we heat up and turn into steam, and there's cooling processes that we use water to actually perform and keep everything running smoothly in power plants. And that water, basically, that hot water gets dumped back into the water reservoir that the power plant is usually next to. So whether it's the ocean or a lake or a river. And what happens there is that the water is a little bit warmer in the regions where that cooling water is being put back into the river or lake or whatever water source. Now, what ends up happening is that the solubility of the oxygen that's inside that lake or river gets decreased, right? So as you increase the temperature, the solubility of the oxygen that's present gets decreased, and basically with decreased oxygen content, animals like fish don't have the appropriate amount of oxygen in the water to be able to run past their gills and subsequently be able to breathe. So this causes problems in the ecosystem if it's not balanced and managed properly. So gas solubility is going to decrease with increase in temperature. The solubility of solids, though, however, generally increase with an increase in temperature. So make sure you're differentiating between gases and solids in terms of their solubility with respect to temperature. Now, pressure and the solubility factors, really, the pressure of a solution doesn't really affect the solubility of liquids or solids. It's not something that's super noticeable. However, gases are affected by pressure. So the solubility of a gas is going to directly be influenced by the pressure of that specific gas. So basically what we see here is a situation in which the gas solubility setup is at equilibrium. So basically particles are exchanging in and out of the solution, but the concentration of the gas dissolved into that solution is constant. The pressure of the gas above the solution is constant, and everything is at equilibrium. Now, when we change this system and basically decrease the volume and subsequently increase the pressure of that gas above the solution, what ends up happening is we disturb this equilibrium. So everything's going to shift in order to reestablish that original concentration. So what's going to happen is that in order to create the same concentration values we had before, more gas is going to dissolve into the liquid. And eventually, equilibrium will be re-established, and you'll have, basically a more concentrated solution with respect to that gas. So the pressure associated with the solubility of gases can be looked at with respect to Henry's law, which basically says that the solubility of a gas is going to be proportional to the pressure of the gas over the solution. So kind of what we already just talked about. However, here's a mathematical representation. S sub G represents the concentration in molarity of the dissolved gas. K is a constant, and it's going to depend on the solvent, solute, and temperature. So that's something that I'll typically give you. And PG is the pressure of the gas over the solution. Okay, so basically what this equation says is that concentration is going to be directly proportional to that pressure. So concentration of that gas above the solution increases. Okay, that usually means that pressure has been increased. Or if I increase the pressure, the concentration of the solution is going to increase. So Henry's law will allow us to figure out things like pressure, or excuse me, things like concentration of the gas in a solution given a specific pressure. So what we're going to be doing here is calculating the solubility, or the concentration rather, of CO2 in a soft drink bottle. Okay, so basically what we're going to do is we're going to use Henry's law. Okay, and we have that situation here. It relates our concentration to our pressure times our constant. Okay, we have been given our constant, so we're going to plug our constant into K. Okay, we're going to plug in our pressure here. We're going to multiply those two together to give us our overall concentration in moles per liter. So basically this equation can be manipulated in whatever way necessary in order to get either our pressure value or our concentration value.